Long before factories and laboratories, humans relied on raw materials to clean their teeth. Crushed bones, shells, and minerals were ground by hand, chosen not by chemistry, by observation.
Tooth enamel is not alive, but it is highly mineralized. Nearly 97% of it is made of calcium-based crystals. To clean teeth without destroying them must mimic enamel's hardness, strong enough to clean, soft enough to protect. Modern toothpaste relies on calcium phosphate, chemically similar to natural enamel. And one of the richest historical sources of this compound comes from animal bones, a material once discarded as waste. In industrial chemistry, bones are not viewed as remains, but as raw material. After food processing, bones are collected, documented, and redirected into material science pipelines, transforming biological waste into functional compounds. Early factories attempted crude processing, grinding bones mechanically, but organic fats and proteins remained trapped inside, causing odor, instability, and contamination. The science wasn't ready yet. The breakthrough came with thermal chemistry. Scientists discovered that extreme heat could strip organic matter entirely, leaving behind pure mineral ash, chemically stable and ideal for controlled abrasion. This discovery laid the foundation for modern toothpaste manufacturing. What began as bone and fire evolved into precision chemistry, regulated, measured, and engineered. And this is only the beginning. The journey begins far from the toothpaste tube. Animal bones enter the system as regulated byproducts from certified food processing facilities. Every batch is logged, traced, and sealed. Without traceability here, the entire process fails before it starts. Bones are fed onto automated sorting lines. Optical scanners and weight sensors detect foreign materials, plastic, metal, or soft tissue remnants, ejecting them instantly. This stage reduces human contact and lowers biological risk. Next comes decontamination. Rotary washing drums tumble the bones while high-pressure jets strip away blood, fat, and surface residue. Mechanical rotation ensures uniform exposure, no blind spots, no shortcuts. Washing is not enough. Bones are sterilized using saturated steam under pressure, often above 120 degrees. This destroys bacteria, spores, and pathogens at the cellular level, without altering the mineral structure inside the bone. Residual fats and marrow are extracted using controlled heat. If left behind, these organics would destabilize later chemical reactions. Precision temperature control prevents mineral damage while fully removing unwanted compounds. Before chemical transformation, moisture must be eliminated. Industrial dryers reduce water content to near zero. Dry material ensures predictable thermal behavior in the next phase, calcination. Final inspections confirm sterility, dryness, and purity. Only bones that meet strict thresholds move forward. Anything else is rejected. At this point, the material is no longer biological, it's mineral feedstock. At this stage, bone stops being waste and enters the realm of thermal chemistry. Automated feeders regulate flow rate with precision. Too fast, and the kiln overloads. Too slow, and chemical conversion becomes incomplete. The rotary kiln is the heart of the process. Rotating continuously, it exposes every fragment evenly to temperatures between 800 and 1000 degrees Celsius. This motion prevents clumping and ensures uniform heat penetration. At these temperatures, organic matter cannot survive. Proteins, fats, and collagen decompose completely, releasing gases and vapor. What remains is mineral, primarily calcium phosphate, the same compound that forms human enamel. Calcination is unforgiving. A deviation of even 50 degrees can change crystal structure. Sensors monitor heat zones along the kiln's length, adjusting fuel and airflow in real time to protect mineral integrity. As organics burn off, gases must be removed immediately. Cyclone separators and baghouse filters capture fine particles, preventing emissions and material loss. Nothing escapes untreated. Once calcination is complete, the material must be cooled quickly. Rapid cooling locks the mineral structure in place, preventing unwanted chemical reactions and preserving consistent abrasiveness. Each batch is chemically verified. X-ray diffraction confirms crystal composition and purity. Only ash that meets strict calcium phosphate profiles moves forward. Calcined ash is now mineral, but still unusable. Its particles are irregular and too large. Automated silos meter the flow into grinding systems with gram-level precision. Any variation here echoes through the entire product. The first reduction happens inside ball mills. As the drum rotates, steel media collide with the ash, breaking it down mechanically. Speed, load, and time determine how aggressively particles fracture. For toothpaste, mechanical grinding alone isn't enough. Jet mills use compressed air to accelerate particles until they collide with each other. No blades, no heat. Just controlled kinetic energy, reducing size to single-digit microns. Too large, and particles scratch enamel permanently. Too small, and cleaning becomes ineffective. The target range is narrow, measured in micrometers. This is the line between dental care and dental damage. Air classifiers act as gatekeepers. Fine particles move forward, oversized material is rejected and recycled back into the mill. Nothing advances unless it meets exact size specifications. Laser diffraction confirms reality. Millions of particles are measured in seconds, generating a size distribution curve. Engineers don't guess, they verify. Each approved batch is assigned an abrasion index, quantifying how aggressively it cleans. This number dictates where the material can be used, sensitive formulas or standard toothpaste. With abrasives engineered at the micron level, toothpaste now becomes a chemical system. Each ingredient is staged separately, stored under controlled temperature and humidity to prevent premature reactions. High-shear mixers do more than blend. Their rotating blades generate controlled turbulence, breaking agglomerates and dispersing particles evenly. Without this shear force, toothpaste would separate inside the tube. Humectants like glycerin and sorbitol bind water molecules, preventing the paste from drying out. Their concentration directly controls shelf life, mouthfeel, and long-term stability. Binders, such as carboxymethylcellulose, activate under shear and hydration. They form microscopic networks that trap abrasives in suspension, preventing sedimentation during months of storage. Fluoride is added last, in precisely metered quantities. Simultaneously, pH probes monitor acidity in real time. Too acidic weakens enamel, too alkaline irritates soft tissue. The acceptable window is narrow. Air is the enemy of consistency. Vacuum deaeration removes trapped bubbles that would otherwise cause tube collapse, inaccurate filling, or bacterial growth over time. Viscosity defines how toothpaste behaves, how it squeezes, spreads, and cleans. Instruments measure resistance under controlled rotation, confirming the paste will behave identically in every tube. Before toothpaste is allowed anywhere near a tube, it is treated as a potential failure. Samples are pulled directly from the production line, sealed, and logged. If the batch fails here, everything behind it is scrapped. Cleaning power must never cross into damage. Robotic brushing machines simulate years of daily use in hours, measuring enamel loss down to microns. This is where abrasive engineering is proven or rejected. Toothpaste contains water, organics, and nutrients, perfect conditions for microbes if formulation fails. Samples are deliberately exposed to bacteria and fungi. Any growth means immediate batch failure. Shelf life isn't guessed, it's accelerated. Temperature cycling simulates years of storage, transport, and bathroom humidity. Separation, thinning, or gas formation disqualifies the product instantly. Active ingredients must remain active. Analytical instruments track fluoride concentration and chemical integrity. If effectiveness degrades, the toothpaste may look fine, but it will never ship. Toothpaste and packaging must coexist. Chemical reactions with tube liners can cause swelling, leakage, or contamination. Mechanical rigs simulate thousands of squeezes to expose hidden weaknesses. Quality control has no gray area. A batch either meets every standard or it is destroyed. Consumers never see these failures, but safety depends on them. After months of preparation, the paste reaches the filling line. High-viscosity pumps maintain continuous flow, monitored by sensors to prevent air pockets or overfilling. Precision here ensures every tube contains exactly the right amount. Filling machines operate at hundreds of tubes per minute. Each nozzle extrudes paste with exact volume. Sealing is critical. Heated rollers trace tube ends. Robotic diverters inspect for proper fill and spurious stability. Sealing is critical. Heated rollers fold and press tube ends, preventing leaks and preserving hygiene. Aluminum tubes require slightly different pressure than plastics, and machines automatically adjust to each material type. Every tube receives a batch code, expiration date, and traceability mark. These identifiers connect back to every stage: bone source, chemical formulation, and quality control results. Traceability ensures safety and accountability. Robotic diverters inspect for proper fill, correct sealing, and label placement. Tubes failing inspection are immediately removed. Automation maximizes efficiency while eliminating human error. Filled tubes are boxed automatically, ensuring protection during transport. Robotics maintain a continuous, precise rhythm, reducing human contact and minimizing contamination risk. From bone to paste to tube, the journey concludes at distribution. Finished product is stored under controlled conditions, ready to reach consumers worldwide, each tube carrying the imprint of science, engineering, and strict quality control. Residual bone dust and organics are captured and repurposed. Sometimes converted as wasted, and each fingerprint of residue undergoes controlled sterilization before reuse. The future is moving towards sustainability. Plant-based and synthetic calcium compounds are increasingly used to reduce dependence on animal byproducts. Engineers ensure these alternatives match the crystal structure and abrasiveness of traditional bone-derived minerals. Modern toothpaste factories are not only measured by output but also energy efficiency. Heat recovery from kilns, optimized airflow in dryers, and renewable energy integration reduce carbon footprint while maintaining chemical and physical quality. Factories increasingly rely on digital twins, virtual replicas of entire production systems. Every conveyor, mixer, and kiln is monitored digitally, ensuring efficiency, safety, and sustainability without interrupting production. Consumers rarely see the source of their toothpaste. Ethical sourcing ensures bones come from regulated food processing, not hunting or unregulated slaughter. Transparency in raw materials is a growing demand in sustainable industry. From bones to paste, and from paste to tube, toothpaste is more than hygiene. It's chemistry, engineering, and responsibility intertwined. The industry continues evolving, striving for products that are safer, cleaner, and sustainable for both people and the planet.